Mathematics has never failed. In the entire history of physics, spanning more than 3 centuries, every phenomenon that has been subjected to mathematical analysis has eventually yielded a finite, meaningful, physically interpretable answer. The motion of planets, the behavior of atoms, the propagation of light, the structure of matter, the expansion of the universe, every question we have asked, mathematics has answered. Every problem we have posed, mathematics has solved. The unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it in 1960, is one of the deepest mysteries of science. Why should the universe be comprehensible through equations at all? And then we point those equations at the center of a black hole, and they break. Not approximately, not subtly, not in a way that can be patched or fixed or adjusted. They produce infinity. They produce a result that has no physical meaning, no physical interpretation, no physical content. The density becomes infinite. The curvature becomes infinite. The tidal forces become infinite. Every quantity that the equations can compute diverges beyond all bounds. The mathematics does not merely struggle, it does not merely approximate, it fails, completely, catastrophically. For the first time in the history of physics, the equations have been asked a question they cannot answer. This failure occurs at the singularity, the point at the center of every black hole where, according to general relativity, all the mass that fell in is compressed into zero volume. The singularity is not a place where our mathematics is insufficient, where we need more computing power or better numerical methods. It is a place where the mathematical framework itself, the language of smooth, continuous functions and differentiable manifolds and tensor calculus, is no longer capable of describing reality. The tools have broken. The language has failed. The map has disintegrated at the very point where we need it most. According to current scientific estimates, the observable universe contains on the order of 100 billion galaxies, each harboring at least one supermassive black hole. Our Milky Way contains Sagittarius A star, with roughly 4 million solar masses and potentially hundreds of millions of stellar mass black holes. Everywhere we look, at every scale, the universe contains objects where our mathematics fails. Not rare objects, not exotic objects, common objects. Objects as ordinary, in cosmic terms, as stars and galaxies. The mathematical failure at the singularity is not an isolated incident. It is a pandemic, occurring at billions of locations throughout the cosmos simultaneously. The failure is not confined to general relativity. When we attempt to apply quantum field theory, our most precise mathematical framework for describing particles and forces, to the extreme conditions near the singularity, it too produces infinities. The quantum vacuum fluctuations near the singularity diverge. The energy density of the quantum fields becomes infinite. The renormalization techniques that tame infinities in ordinary quantum field theory fail at the Planck scale. Both of our greatest mathematical frameworks for describing nature break simultaneously at the same point. By the end of tonight, you are going to understand why mathematics fails inside black holes, what the failure means, what it tells us about the nature of mathematics and the nature of reality, and what the leading proposals for fixing the failure look like. You are going to confront the possibility that the failure is not a flaw in our mathematics, but a signal, a message from the universe telling us that the mathematical language we have been using, the language of smooth, continuous spacetime, is not the right language for describing reality at its most extreme. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The failure of mathematics inside black holes is not a problem for mathematicians. It is a problem for reality. Because if mathematics is the language of nature, and if that language fails at the singularity, then either nature has a feature that lies beyond the reach of mathematics, or we are using the wrong mathematics. Either possibility is profound. Either possibility will reshape our understanding of the universe, and either possibility is being actively explored by the most creative minds in theoretical physics. The mathematical failure is also deeply personal. If you fell into a supermassive black hole, The mathematics that describes your trajectory would work perfectly for the entire journey from the event horizon toward the center. Your path through spacetime would be described with exquisite precision by the geodesic equations of general relativity. The tidal forces on your body would be calculated exactly. The visual distortions you would see would be predicted with mathematical perfection. And then, at the center, the equations would produce infinity. Your density would become infinite. Your volume would become zero. Every physical quantity associated with your existence would diverge. The mathematics that described your journey with such precision would, at the final moment, produce an answer that has no physical meaning. The map would dissolve at the destination. The language would fail at the most important word. The universe contains, at conservative estimates, trillions of singularities. Each one is a place where the most powerful mathematical framework in the history of science produces a result that has no physical meaning. Each one is a gap in our mathematical description of reality. Each one is a challenge, patient and silent, waiting for the mathematical language that will finally describe what happens at the center. The scale of the mathematical failure is not local, it is cosmic. And the resolution, when it comes, will be equally cosmic in its implications. The singularity is not merely a challenge for theoretical physics. It is a challenge for the concept of mathematical description itself. It asks whether mathematics can describe everything, or whether there are aspects of reality that lie beyond any mathematical framework we can construct. Now, let us begin. To understand why mathematics fails inside black holes, we must first understand the mathematics that fails. We must understand general relativity, its mathematical structure, its extraordinary precision, and the exact mechanism by which it produces the singularity. Because the failure is not random or arbitrary. It is precise, specific, and deeply connected to the fundamental assumptions of the theory. Understanding the failure requires understanding the success that precedes it. General relativity is a theory of geometry. It describes gravity not as a force, but as the curvature of spacetime. The mathematical framework is differential geometry, the study of curved spaces, of manifolds, of metrics, of tensors. The central object is the metric tensor, a mathematical object that encodes the geometry of spacetime at every point, specifying the distances between nearby events, the angles between nearby directions, the relationship between space and time at every location. Einstein's field equations relate the geometry of spacetime, encoded in the Einstein tensor, to the distribution of mass and energy, encoded in the stress-energy tensor. The equations are 10-coupled, non-linear partial differential equations. They are extraordinarily difficult to solve. Exact solutions exist only for highly symmetric cases, but the solutions that have been found are among the most important results in the history of physics. The first exact solution was found by Carl Schwarzschild in 1916. Schwarzschild was serving on the Eastern Front of the First World War and suffering from a fatal autoimmune disease called pemphigus when he derived his solution. He solved Einstein's equations for the simplest case, a perfectly spherical, non-rotating, uncharged mass in vacuum. His solution describes the geometry of spacetime around such an object with mathematical precision. The Schwarzschild solution is expressed in terms of the Schwarzschild coordinates, time, radial distance, and two angular coordinates. In these coordinates, the metric takes a specific form that depends on the mass of the central object and the radial distance from the center. At the Schwarzschild radius, roughly 1.86 miles for a solar mass object, the metric coefficient in front of the time coordinate vanishes, and the coefficient in front of the radial coordinate diverges. At the radial coordinate of 0, the center, the curvature and variance diverge. These two features, the coordinate singularity at the Schwarzschild radius and the curvature singularity at the center, define the mathematical structure of the black hole. The coordinate singularity at the Schwarzschild radius is not a genuine failure of mathematics. It is an artifact of the choice of coordinates, analogous to the apparent singularity at the North Pole in latitude-longitude coordinates. David Finkelstein showed in 1958 that the Schwarzschild radius is a smooth, well-behaved surface when described in appropriate coordinates. The event horizon is not a place where mathematics fails. It is a place where one particular coordinate system fails, while the underlying geometry remains smooth and regular. The curvature singularity at the center is a different matter entirely. This singularity is not an artifact of any coordinate choice. It is a genuine feature of the geometry. The Kretschner scalar, a coordinate-independent measure of the curvature of spacetime, diverges at the center. This divergence is present in every coordinate system. It cannot be removed by any change of variables. It is a genuine mathematical infinity, a point where the equations of general relativity produce a result that has no physical interpretation. The curvature at the singularity of a Schwarzschild black hole is inversely proportional to the cube of the distance from the center and proportional to the mass. As the distance approaches zero, the curvature approaches infinity. The tidal forces, which stretch objects in one direction and compress them in another, also diverge. The Riemann curvature tensor, which encodes the complete information about the curvature at each point, has components that diverge at the center. The mathematical language used to describe general relativity is differential geometry on smooth manifolds. A manifold is a mathematical space that locally looks like ordinary flat space. It can be curved, twisted, folded, but it must be smooth, continuous, differentiable. The metric tensor is a smooth function defined at every point. The curvature tensors are derived from the metric through differentiation, and they too must be smooth and well defined at every point. At the singularity, this smoothness breaks. The metric is not well defined. The curvature is infinite. The smooth manifold structure, the foundation of the entire mathematical framework, ceases to exist. But here is the problem. The singularity is not a point in the manifold. It is the boundary of the manifold, the edge beyond which the mathematical description cannot be extended. General relativity does not describe what happens at the singularity. It describes everything up to the singularity and then stops. The Penrose-Hawking singularity theorems, proven in the mid-1960s, establish that this failure is not an artifact of the Schwarzschild solution's perfect symmetry. Roger Penrose proved in 1965 that singularities are unavoidable consequences of general relativity under very general conditions. The proof requires only three assumptions: that general relativity is correct, that the energy density of matter is positive, and that a trapped surface has formed. Once these conditions are met, geodesic incompleteness follows. There must be world lines that terminate after finite proper time. There must be a singularity. Penrose's proof was topological, using mathematical techniques from algebraic topology that had never before been applied to general relativity. Stephen Hawking extended the methods and proved more general theorems. Together, the Penrose-Hawking theorems showed that the mathematical failure at the singularity is generic, unavoidable, and robust. No amount of asymmetry, rotation, perturbation, or realistic physical conditions can prevent it. The mathematics fails under the most general circumstances imaginable. The global positioning system provides a vivid illustration of how well general relativistic mathematics works everywhere except at the singularity. GPS satellites orbit at roughly 12,500 miles above the Earth. The gravitational time dilation and the velocity time dilation must be calculated with extraordinary precision using general relativity. Without these corrections, GPS positions would drift by roughly 10 kilometers per day. Every smartphone, every car navigation system, every aircraft guidance computer relies on general relativistic mathematics working perfectly. The Event Horizon Telescope photographed the shadow of M87 star in 2019, confirming that the exterior geometry matches the predictions of general relativity with high precision. The LIGO Observatory has detected roughly 90 gravitational wave events from merging black holes, each one confirming the mathematical predictions of general relativity for the spacetime geometry outside the event horizon. Andrea Ghez and Reinhard Genzel tracked stars orbiting Sagittarius A star for more than 2 decades, earning the Nobel Prize in 2020. Every observation confirms that general relativistic mathematics works with extraordinary precision outside the singularity. The mathematical framework of general relativity has been tested in domains far beyond the weak field limit of everyday gravity. The binary pulsar PSRB 1913+16, discovered by Russell Hulse and Joseph Taylor in 1974, provided the first confirmation of gravitational wave emission. The orbital decay of the binary system matched the prediction of general relativity to better than 1/3 of 1%. This earned Hulse and Taylor the Nobel Prize in 1993. The LIGO detection of gravitational waves from merging black holes in 2015 provided a direct test of general relativistic mathematics in the strong field regime, where gravitational effects are extreme. The waveforms of the detected signals match numerical solutions of Einstein's equations with remarkable precision. The chirp mass, the spin parameters, the ring-down frequencies all match the mathematical predictions. The ring-down phase, when the merged black hole vibrates and settles into its final state, tests the no-hair theorem, confirming that the final object is consistent with the Kerr solution. The mathematical framework describes the exterior of black holes with such precision that any proposed modification to general relativity is tightly constrained by observations. The parameterized post-Newtonian framework, which describes deviations from general relativity in a systematic way, has been used to constrain a wide range of alternative theories. All observations are consistent with general relativity to the precision of current measurements. The photon sphere at 1.5 Schwarzschild radii, where light can orbit the black hole, illustrates the mathematical precision of general relativity near the event horizon. The photon sphere is a prediction of the Schwarzschild solution, and it has been confirmed indirectly through observations of relativistic jets and accretion disk emissions. The photon ring, a sharp, bright feature just outside the event horizon, is predicted to encode detailed geometric information about the near-horizon spacetime. Future Event Horizon Telescope observations may resolve this feature, providing another test of general relativistic mathematics. The mathematical precision extends even closer to the event horizon. The innermost stable circular orbit, located at 3 Schwarzschild radii for a non-rotating black hole, is the closest stable orbit. Inside this radius, no stable circular orbit exists. Matter must either escape outward or fall in. The properties of accretion disks are determined by this radius, and X-ray observations of accreting black holes are consistent with the general relativistic predictions. The mathematical success of general relativity from the innermost stable circular orbit to the event horizon, a distance of 1.5 Schwarzschild radii, is confirmed by observations. The mathematics works perfectly at the event horizon itself, where the coordinate singularity can be removed by a change of coordinates. The mathematics continues to work inside the event horizon, describing the inversion of space and time, the contraction of spatial dimensions, the approach to the singularity, and then, at the center, it fails. The contrast between the mathematical success outside and the mathematical failure inside could not be more dramatic. The same equations that predict gravitational waves to extraordinary precision produce infinity at the center. The same tensor calculus that describes the curvature of spacetime around a binary pulsar produces a curvature that diverges to infinity at the singularity. The mathematical language is the same. The physical regime is different, and the regime where the mathematics fails is the most extreme regime in the universe. The mathematical failure is related to the concept of geodesic incompleteness. In a smooth manifold, geodesics, the paths that particles follow through spacetime, can be extended indefinitely in both directions. In a spacetime with a singularity, some geodesics cannot be extended beyond a finite affine parameter. They terminate. They have finite length. They reach the singularity and stop. The spacetime is geodesically incomplete. Geodesic incompleteness is the technical definition of a singularity in general relativity. It is the mathematical statement that the manifold has a boundary, an edge, a point beyond which the smooth structure cannot be continued. The Penrose-Hawking singularity theorems prove that geodesic incompleteness is unavoidable under general conditions. The mathematics of smooth manifolds cannot describe what happens at the edge. The smooth structure terminates. The calculus stops. The equations have no domain to operate in. The Kruskal-Zikaras extension of the Schwarzschild solution provides the maximal analytic extension of the spacetime, the largest smooth manifold that is consistent with the vacuum Einstein equations and the Schwarzschild symmetry. Even in this maximal extension, the singularity is present. The spacetime cannot be extended through the singularity. The smooth manifold has reached its limit. The mathematics can go no further. For a rotating black hole, described by the Kerr solution found by Roy Kerr in 1963, the interior is more complex. The Kerr solution has two horizons and a ring singularity. The maximal analytic extension of the Kerr solution includes regions that can be interpreted as other universes, connected through the ring singularity. But the inner Cauchy horizon is almost certainly unstable, destroyed by the mass inflation instability discovered by Werner Israel and Eric Poisson. The mathematical structure of the Kerr interior is rich and elaborate, but it is also fragile, unable to survive contact with realistic perturbations. The mathematical failure at the singularity is connected to the cosmic censorship conjecture proposed by Roger Penrose in 1969. Cosmic censorship states that singularities formed by gravitational collapse are always hidden behind event horizons. If cosmic censorship holds, the mathematical failure is quarantined. The outside universe never sees it. The mathematics works perfectly outside the horizon, and the failure is sealed away inside. But cosmic censorship has never been proven, in full generality. Its truth or falsity remains one of the great open problems in mathematical physics. The precision of general relativity everywhere else makes the failure at the singularity all the more striking. The theory predicts gravitational waves to 14 significant figures of accuracy. It predicts the precession of Mercury's orbit to 6 significant figures. It predicts the bending of starlight by the sun to extraordinary precision. And then, at one specific point, at the center of every black hole, this same theory produces infinity. The most precise mathematical theory in the history of science produces, at one specific location, an answer that has no meaning whatsoever. The most successful mathematical language ever developed encounters, at one specific point, a question it cannot answer. The most powerful mathematical tools ever forged break at one specific target. The failure is not a minor blemish on an otherwise perfect record. It is a catastrophic breakdown at the most important point, the most extreme conditions, the most fundamental regime. The failure is not gradual. It is not a matter of decreasing precision as you approach the center. The mathematics works perfectly, all the way down, to an infinitesimally small distance from the singularity. At any finite distance, no matter how small, the equations produce a finite, meaningful answer. Only at the singularity itself, at zero distance, does the answer diverge. The transition from success to failure is not gradual but instantaneous, occurring at a single mathematical point. The Schwarzschild radius scales linearly with mass. For our Sun, it is roughly 1.86 miles. For Sagittarius A star, roughly 7.5 million miles. 2. For M87 star, roughly 12 billion miles, larger than the orbit of Pluto. The event horizon is not where mathematics fails. The mathematics works perfectly at the event horizon. Mathematics fails only at the center, at the singularity, at the point of zero radial distance. The density at the singularity is predicted to be infinite. For a stellar mass black hole of 10 solar masses, this means roughly 20,000 billion kilograms of matter compressed into zero volume. The density is not merely large, it is not merely enormous, it is infinite. An infinite density is not a physical prediction, it is a mathematical breakdown. For comparison, the density of a neutron star, the densest stable object we can observe, is roughly 500 million tons per cubic centimeter. The Planck density, where quantum gravitational effects are expected to dominate, is roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. An enormous number, but critically not infinity. The gap between neutron star density and the Planck density spans roughly 78 orders of magnitude. The gap between the Planck density and the Singularity's infinite density is itself infinite. Somewhere in that infinite gap, the mathematics of general relativity has been pushed beyond its domain of validity. The equations continue to produce answers, but the answers have stopped being physically meaningful. The density at the event horizon provides an instructive perspective on the mathematical precision of general relativity. For a stellar mass black hole of 10 solar masses, the average density at the event horizon is roughly 200 million tons per cubic centimeter. For Sagittarius A star, with 4 million solar masses, the density at the horizon is roughly 1,000 kilograms per cubic centimeter, comparable to a dense metal. For M87 star, with 6.5 billion solar masses, the density at the horizon is less than the density of air. The mathematics works perfectly at all of these densities, producing finite, meaningful, physically interpretable answers. The tidal forces at the event horizon also vary with mass. For a stellar mass black hole, the tidal forces at the horizon are extreme, strong enough to spaghettify a human body. For a supermassive black hole, the tidal forces at the horizon are negligible. The mathematics describes these tidal forces with perfect precision at the horizon, regardless of the mass. Inside the event horizon, the mathematics continues to work. The Schwarzschild interior describes the inversion of space and time. The radial direction becomes time-like. The singularity becomes a future moment rather than a spatial location. The mathematics describes this inversion perfectly. The metric tensor changes sign. The light cones tilt inward. The geodesics curve toward the center. All of this is described with mathematical precision by the equations of general relativity. The proper time from the event horizon to the singularity is finite and calculable. For Sagittarius A star, it is roughly 20 seconds. For M87 star, it could be hours. The mathematics calculates this time exactly, using the geodesic equations of the Schwarzschild metric. The mathematics works perfectly for every moment of the journey from the horizon to the center. It works at the horizon. It works a microsecond before the singularity. It works a nanosecond before. It works a picosecond before. Only at the singularity itself does the mathematics fail. The failure is instantaneous and total. The visual experience of the interior has been computed numerically using the mathematical framework of ray tracing in curved spacetime. The results are extraordinary. The falling observer sees the outside universe compressed into a shrinking circle of blue shifted light above, below, darkness. Multiple images of distant stars appear at different positions. The visual field is a hall of distorted mirrors. All of this is calculated with mathematical precision by the equations of general relativity. The mathematics works perfectly for computing what the observer sees at every moment of the fall, until the singularity. The BKL dynamics near the singularity reveal the mathematical complexity of the approach to the failure point. The geometry oscillates chaotically, contracting in one direction while expanding in another. The oscillations become faster and more violent. The Kretschmer scalar, the curvature invariant, grows without bound. The mathematical description becomes increasingly complex, increasingly chaotic, but remains well-defined at every finite distance from the center. The failure occurs only at the center itself, at zero distance, at the precise mathematical point where the curvature diverges. The contrast between the mathematical precision everywhere else and the mathematical failure at the center is the defining feature of the singularity problem. General relativity is not a theory that works approximately. It is a theory that works exactly, with extraordinary precision, verified by observations spanning decades, and it contains, within its own equations, the proof of its own incompleteness. The singularity is the theory's confession that it cannot describe everything, that at one specific point, under one specific set of conditions, its mathematical language runs out of words. The concept of geodesic incompleteness, the technical definition of the singularity, illustrates the nature of the mathematical failure. In a smooth manifold, geodesics can be extended indefinitely. In a spacetime with a singularity, some geodesics terminate after finite affine parameter. They have finite length. They reach the singularity and stop. The spacetime is geodesically incomplete. The mathematical framework of smooth manifolds cannot describe what happens at the termination point. The framework has reached its boundary. The mathematics stops. The Kruskal-Szekeres coordinates provide the maximal analytic extension of the Schwarzschild spacetime. In these coordinates, the event horizon is smooth and well-behaved. The full causal structure of the spacetime is revealed, but the singularity remains. The maximal extension includes the singularity as a boundary. The spacetime cannot be extended through it. The mathematics has been pushed to its maximum extent, and the singularity is the limit. For a rotating Kerr black hole, the maximal extension is more elaborate. There are two horizons, an outer event horizon and an inner Cauchy horizon. The singularity is a ring. The mathematical structure permits paths through the ring into different spacetimes, but the inner horizon is almost certainly unstable, destroyed by the mass inflation instability. The mathematical elegance of the Kerr extension is a casualty of physical realism. The cosmic censorship conjecture states that singularities are always hidden behind event horizons. If true, the mathematical failure is quarantined. The mathematics works perfectly outside the horizon, and the failure is sealed inside. But cosmic censorship remains unproven. The mathematical failure may, under extreme conditions, be visible to the outside universe. A naked singularity would be a mathematical failure exposed to direct observation, a point of infinite curvature visible to distant observers. The relationship between the mathematical success of general relativity and its failure at the singularity illuminates the nature of mathematical approximation in physics. Every successful mathematical framework in physics has a domain of validity. Newtonian mechanics works perfectly at speeds much less than the speed of light. Special relativity works perfectly for flat spacetime. Quantum mechanics works perfectly for non-gravitational systems. Each framework works within its domain and fails outside it. General relativity works perfectly for smooth spacetime with moderate curvature and fails at the singularity, where the curvature diverges. The mathematical concept of a domain of validity is crucial. The mathematics does not suddenly become wrong at the boundary of its domain. It becomes increasingly imprecise, increasingly unreliable, increasingly prone to producing unphysical results. Near the boundary, the mathematics still gives approximately correct answers. At the boundary, the approximation breaks down. Beyond the boundary, the mathematics produces nonsense, infinities, physically meaningless results. For general relativity, the boundary is the Planck scale. Below the Planck density, the smooth manifold mathematics provides an extraordinarily precise description of spacetime. Above the Planck density, the description fails. The singularity, which occurs at infinite density, is far beyond the boundary. The mathematics at the singularity is not just imprecise, it is completely wrong. The infinite density predicted by general relativity is a mathematical artifact of applying the smooth manifold framework far beyond its domain of validity. The history of physics is filled with examples of this pattern. Newtonian mechanics predicts that velocities can be arbitrarily large. Special relativity corrects this. The speed of light is the upper limit. Classical electromagnetism predicts that a hot object radiates infinite energy at short wavelengths, the ultraviolet catastrophe. Quantum mechanics corrects this. The energy is quantized. In each case, the old framework produces an infinity that is resolved by a new framework with a broader domain of validity. The mathematical failure at the singularity follows the same pattern. General relativity predicts infinite density. Quantum gravity will correct this. The Planck density is the upper limit. The infinity is an artifact of the old framework. The new framework will produce a finite answer. The pattern is clear, consistent, and historically well established. The no-hair theorem provides a mathematical perspective on the information content hidden behind the event horizon. The exterior is described by three numbers. The interior has 10 to the power of 77 microstates. The smooth manifold mathematics can describe the exterior with three numbers. It cannot describe the interior with 10 to the power of 77 microstates. The mathematical failure at the singularity is connected to this gap between macroscopic simplicity and microscopic complexity. The smooth manifold framework does not have the mathematical capacity to encode the full microscopic description. A richer mathematical framework is needed. The connection between the mathematical failure and the thermodynamics of black holes provides crucial constraints. The Bekenstein-Hawking entropy assigns a finite entropy to every black hole proportional to the horizon area. The Hawking temperature is finite and inversely proportional to mass. The four laws of black hole mechanics mirror the four laws of thermodynamics. These thermodynamic relationships are mathematically well defined at the horizon and inconsistent with a singularity of infinite density at the center. The finite exterior thermodynamics demands a finite interior structure. The mathematical infinity at the singularity contradicts the mathematical finiteness of the exterior thermodynamics. The information paradox, discovered by Stephen Hawking in 1974, is a direct consequence of the mathematical failure. If the mathematics breaks at the singularity, the information encoded in infalling matter is destroyed. Unitarity, the quantum mechanical principle that information is always preserved, is violated. The mathematical failure at the singularity causes a cascading failure in quantum mechanics. The two mathematical frameworks are incompatible at the singularity. The Hawking temperature of a solar mass black hole is roughly 60 billionths of a Kelvin. The evaporation time is roughly 10 to the power of 67 years. The evaporation time for supermassive black holes stretches to 10 to the power of 100 years. These timescales, calculated with mathematical precision by general relativity and quantum field theory, tell us that the black hole is not eternal. It will evaporate. And the evaporation must be consistent with either unitarity or its violation. The mathematical failure at the singularity determines which. The no-hair theorem highlights the mathematical tension between exterior simplicity and interior complexity. The exterior is described by three numbers. The interior has 10 to the power of 77 microstates. The smooth manifold mathematics can describe the simple exterior perfectly. It cannot describe the complex interior. The mathematical failure at the singularity is connected to this gap. The three-number description is too simple to encode 10 to the power of 77 microstates. A richer mathematical framework is needed. The Strominger-Waffe accounting of 1996 provided the first explicit microscopic accounting of the Bekenstein-Hawking entropy within string theory. For a specific class of extremal black holes, the number of string-theoretic microstates matches the macroscopic entropy formula exactly. This counting demonstrated that the microstates are real, that they can be counted, and that the mathematical framework of string theory has the capacity to describe them. The smooth manifold of general relativity cannot count these microstates. The string-theoretic framework can. The accretion disks around black holes provide observational evidence for the extreme conditions near the event horizon. X-ray spectroscopy reveals gravitationally redshifted emission lines from the inner disk. The redshift is consistent with emission from within a few Schwarzschild radii. The mathematical predictions of general relativity for the disk spectrum are confirmed. The mathematics works perfectly in the vicinity of the event horizon. It fails only at the center. Most physicists believe unitarity is preserved. The mathematical failure at the singularity is an artifact of the smooth manifold framework, not a genuine physical event. The correct mathematical framework will produce finite answers at the center and preserve information. The island formula, developed in 2019 and 2020, confirmed that the entropy of Hawking radiation follows the Page curve, the mathematical signature of unitary evolution. Information is preserved. The mathematical failure is resolved in the quantum theory. But what scientists discovered next was worse than anyone expected. The core problem is not simply that general relativity produces infinity at the singularity. Infinities have appeared in physics before and have been successfully tamed. The infinities in quantum electrodynamics, the quantum theory of light and electrons, were tamed by the renormalization program developed by Richard Feynman, Julian Schwinger, Sine Itiro Tomonaga, and Freeman Dyson in the 1940s. The infinities in the electroweak theory were tamed by the work of Gerard Hooft and Martinus Veltman in the early 1970s. Infinities, in physics, are often signs that a theory needs to be refined, not replaced. The refined theory produces finite answers, where the old theory produced infinities. But the infinity at the singularity of a black hole is different. It is worse. It is qualitatively different from the infinities that have been successfully tamed in quantum field theory. And understanding why it is different is the key to understanding why mathematics fails inside black holes. In quantum field theory, infinities arise from the contributions of virtual particles at very short distances, very high energies, very high momenta. These are called ultraviolet divergences. They can be tamed by renormalization, a systematic procedure for absorbing the infinities into the definitions of physical quantities like mass and charge. The procedure works because the infinities are of a specific mathematical form. They are logarithmic or polynomial in the cutoff energy. They can be absorbed into a finite number of parameters, and the remaining predictions are finite and extraordinarily precise. General relativity is not renormalizable. The infinities that arise when you try to quantize general relativity cannot be absorbed into a finite number of parameters. Each order of perturbation theory introduces new types of infinities that require new parameters to absorb them. The number of parameters grows without bound. The theory loses its predictive power. The mathematical procedure that works so brilliantly for quantum electrodynamics and the electroweak theory fails completely for gravity. This non-renormalizability is a mathematical statement about the structure of general relativity as a quantum theory. It tells us that the mathematical framework of perturbative quantum field theory, the framework that has been so spectacularly successful for the other forces of nature, cannot accommodate gravity. The mathematical language is not rich enough. The tools are not powerful enough. A new mathematical framework is needed. The singularity at the center of a black hole is the most dramatic manifestation of this mathematical failure. It is the place where the classical theory produces infinity and where the quantum theory cannot even be formulated consistently. The classical infinity at the singularity and the quantum non-renormalizability of gravity are two aspects of the same fundamental problem. The mathematical language of smooth, continuous, differentiable functions on a smooth manifold is not the right language for describing gravity at extreme scales. And it gets worse. The mathematical failure at the singularity is not confined to a single quantity. Every physical quantity diverges. The curvature, the density, the tidal forces, the temperature. Every observable that general relativity can compute produces infinity at the singularity. The failure is total. The mathematics does not merely struggle with one aspect of the physics. It fails at everything. The BKL dynamics, discovered by Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz, reveal the full complexity of the mathematical failure near the singularity. Near a generic singularity, the geometry of spacetime oscillates chaotically. Space contracts in one direction while expanding in another, then switches. The oscillations become more rapid and more violent as the singularity is approached, their frequency approaching infinity. Charles Misner called this mixmaster dynamics. The approach to the singularity is not a smooth, gentle convergence. It is a chaotic, violent, increasingly frenzied convulsion of spacetime. The mixmaster oscillations are mathematically equivalent to the motion of a billiard ball in a triangular domain with specific angles. The ball bounces between the walls an infinite number of times as the singularity is approached. Each bounce corresponds to a change in the pattern of spatial contraction and expansion. The dynamics are chaotic, meaning that tiny differences in initial conditions lead to exponentially divergent trajectories. The singularity is not just infinite, it is chaotically infinite. The mathematical failure is not just a simple divergence, it is a divergence wrapped in chaos. The Weil curvature hypothesis, proposed by Roger Penrose, connects the mathematical failure at the singularity to the arrow of time. Penrose observed that the initial singularity of cosmological models has low Weil curvature, while the singularities inside black holes have high Weil curvature. The Weil tensor measures the component of curvature that is not directly caused by the local matter distribution. The difference in Weil curvature between the two types of singularities reflects the difference in entropy. The initial singularity has low entropy, while the black hole singularity has high entropy. This connection suggests that the mathematical failure at the singularity is intimately connected to the thermodynamic properties of the black hole. The Bekenstein-Hawking entropy, proportional to the area of the event horizon, tells us that the black hole has an enormous number of microstates. For a solar mass black hole, the entropy is roughly 10 to the power of 77. The mathematical failure at the singularity is somehow related to this enormous internal complexity. The mathematics fails where the complexity is greatest. The no-hair theorem adds another dimension. The exterior of a black hole is mathematically simple, described by just three numbers: mass, charge, and spin. The interior is mathematically complex, with 10 to the power of 77 microstates. The mathematical failure at the singularity is the point where the simple exterior description and the complex interior description collide. The mathematics of smooth manifolds and continuous functions can describe the simple exterior perfectly. It cannot describe the complex interior. The information paradox, discovered by Stephen Hawking in 1974, is a direct consequence of the mathematical failure. If the mathematics breaks down at the singularity, and if matter falls through the event horizon and reaches the singularity, then the quantum state of that matter is compressed into a point where the mathematics fails. The information encoded in the quantum state is destroyed because the mathematical framework that would describe its evolution has broken down. Unitarity, the quantum mechanical principle that information is always preserved, is violated. Most physicists believe the information is not destroyed. The mathematical failure at the singularity is an artifact of using the wrong mathematics, not a genuine physical feature. The correct mathematics, whatever it turns out to be, will produce finite answers at the center and preserve information throughout the process. The death of information at the singularity is not a physical event. It is a symptom of a mathematical disease, a disease that will be cured when the right mathematical framework is found. The Heisenberg uncertainty principle provides a direct argument that the classical mathematical failure cannot be physically real. At the singularity, matter is compressed into zero volume. The uncertainty in position is zero. But the uncertainty principle says that if position is known exactly, momentum must be infinitely uncertain, implying infinite kinetic energy and infinite pressure resisting further compression. The quantum mechanical mathematics contradicts the general relativistic mathematics at the singularity. Both cannot be right. At least one must be using the wrong mathematical framework. The Planck scale is the natural boundary between the domains of the two mathematical frameworks. The Planck length, roughly 10 to the power of negative 35 meters, is the scale at which quantum gravitational effects become important. The Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, is the density at which the smooth manifold description of spacetime is expected to break down. Above this density, the correct mathematical description is unknown. Below it, general relativity works perfectly. The gap between the Planck scale and our experimental capabilities is vast. The smallest distances probed by the Large Hadron Collider are roughly 10 to the power of negative 18 meters, roughly 17 orders of magnitude larger than the Planck length. No foreseeable technology can bridge this gap directly. The mathematical framework that replaces general relativity at the singularity must be discovered through theoretical reasoning, through mathematical consistency arguments, and through the constraints provided by the information paradox, the holographic principle, and the thermodynamics of black holes. The relationship between the mathematical failure and quantum mechanics is the deepest aspect of the problem. Quantum mechanics is formulated in the mathematical language of Hilbert spaces, linear operators, and unitary evolution. This mathematical framework is extraordinarily successful, predicting the behavior of atoms, molecules, particles, and fields with unparalleled precision. The anomalous magnetic moment of the electron is predicted by quantum electrodynamics to more than 12 decimal places of accuracy. No other theory in the history of science has achieved such mathematical precision. But the mathematical framework of quantum mechanics assumes a fixed, smooth, classical space-time background. The Schrödinger equation evolves the quantum state in time. The time is a parameter, a coordinate on a smooth manifold. The quantum fields are defined on this smooth background. The mathematics of quantum mechanics is built on the assumption that the space-time on which it operates is smooth and well-defined. At the singularity, this assumption fails. The space-time is not smooth. The manifold has a boundary. The metric diverges. The coordinates are not well-defined. The mathematical framework of quantum mechanics, which assumes a smooth background, cannot operate at a point where the background has broken down. The mathematical failure of general relativity causes a cascading mathematical failure in quantum mechanics. Both frameworks fail simultaneously, for related but distinct mathematical reasons. The Wheeler-DeWitt equation, one of the earliest attempts to formulate quantum gravity, illustrates the mathematical challenge. The equation attempts to describe the quantum state of the universe without assuming a fixed background spacetime, but it has no time variable. The equation is static. Time must be reconstructed from the quantum state, not assumed as a background parameter. This is the problem of time in quantum gravity, one of the deepest mathematical challenges in the field. The non-renormalizability of general relativity is the quantum mechanical manifestation of the mathematical failure. When physicists try to quantize general relativity using the standard perturbative methods that work for other forces, the calculation produces infinities that cannot be absorbed into a finite number of parameters. Each order of perturbation theory introduces new types of infinities, requiring new parameters. The theory becomes mathematically unpredictive. The perturbative mathematical framework that works brilliantly for electromagnetism, the weak force, and the strong force fails for gravity. This non-renormalizability is connected to the classical singularity through the concept of ultraviolet divergences. The singularity is a classical ultraviolet divergence, a divergence at short distances. The quantum non-renormalizability is a quantum ultraviolet divergence, a divergence at high energies. Both are manifestations of the same underlying problem. The mathematical language of smooth, continuous functions on smooth manifolds is not adequate for describing gravity at extreme scales. The Planck scale marks the boundary between the mathematical domains. Below the Planck density, the smooth manifold mathematics works. Above it, the smooth manifold mathematics fails. The Planck length, the Planck time, the Planck density are the mathematical frontier markers. They tell us where the old mathematics ends and where the new mathematics must begin. The gap between the Planck scale and our experimental reach is the most important gap in all of physics. It is roughly 17 orders of magnitude wide. Bridging it through direct experiment would require an accelerator, roughly a light year in diameter. The mathematical framework that describes gravity at the Planck scale must be discovered through mathematical reasoning alone, constrained by consistency requirements, by the information paradox, by black hole thermodynamics, and by the handful of indirect observational constraints available. The connection between the mathematical failure at the singularity and the holographic principle provides the most powerful perspective on the nature of the failure. The holographic principle states that the maximum information content of any region of space is proportional to the area of its boundary, not its volume. This is a mathematical statement about the dimensionality of the fundamental description. The fundamental description is two-dimensional. The three-dimensional description is derived. If the three-dimensional smooth manifold of general relativity is derived, secondary, approximate, then the mathematical failure at the singularity is a failure of the derived description, not of the fundamental one. The fundamental two-dimensional description, the boundary quantum field theory in the ADS CFT framework, is perfectly well defined. It has no singularity. It has no mathematical failure. The mathematics works perfectly in the fundamental description. The failure occurs only in the translation from the fundamental two-dimensional description to the derived three-dimensional description. This perspective transforms the question of why mathematics fails. The mathematics does not fail in the fundamental description. It fails in the derived description. The smooth manifold of general relativity is a derived mathematical object generated by the entanglement structure of the boundary quantum state through a holographic encoding. At the singularity, the encoding breaks down. The derived description develops a singularity, but the fundamental description continues smoothly. The Ryuta-Kayanagi formula makes the connection between entanglement and geometry mathematically precise. The entanglement entropy of a boundary region equals the area of the minimal bulk surface divided by 4 in Planck units. This formula encodes the mathematical rule by which the boundary entanglement generates the bulk geometry. The formula works perfectly when the entanglement structure supports a smooth geometry. At the singularity, the entanglement structure has been disrupted beyond the capacity of the formula to generate a smooth geometric output. The formula still exists. The entanglement still exists. But the geometric output has broken down. The quantum error correcting code structure provides the mathematical mechanism. The bulk geometry is encoded in the boundary through a code. Away from the singularity, the code is robust, redundant, error-resistant. The geometric description is reliable. Near the singularity, the code degrades. The redundancy decreases. The error resistance weakens. At the singularity, the code has failed. The geometric description has no content. The mathematical failure is a failure of the code, not of the underlying quantum state. The gravitational path integral, which sums over all possible spacetime geometries, provides another perspective. Individual classical geometries may contain singularities, but the quantum sum over all geometries, including exotic contributions from replica wormholes, produces finite, well-defined answers. The singularity is washed out by the quantum sum. The mathematical failure occurs in individual classical geometries but not in the full quantum theory. This is analogous to quantum tunneling. In classical mechanics, a particle cannot cross a potential barrier higher than its energy. The classical mathematics predicts that the particle is reflected. But quantum mechanics, which sums over all possible paths, includes paths that tunnel through the barrier. The quantum sum produces a finite probability of tunneling. Similarly, the quantum gravitational path integral sums over all geometries, including those that avoid the singularity. The quantum sum produces finite answers where individual classical geometries produce infinities. The thermodynamic constraints from the Bekenstein-Hawking entropy provide a quantitative check on any proposed resolution. The entropy of a solar mass black hole is roughly 10 to the power of 77. This number constrains the mathematical framework. Any framework that resolves the singularity must accommodate this number of microstates. A singularity of infinite density and zero volume cannot accommodate microstates. The entropy demands mathematical structure at the center. The singularity denies it. The entropy wins. The 4 laws of black hole mechanics, established by Bardeen, Carter, and Hawking, mirror the 4 laws of thermodynamics and provide additional mathematical constraints. The Hawking temperature is inversely proportional to mass. The Bekenstein-Hawking entropy is proportional to area. These relationships must be reproduced by any mathematical framework that resolves the singularity. The thermodynamic constraints are powerful, independent, and complementary to the unitarity constraints. The scrambling time tells us how fast the mathematical description of the interior dynamics operates. For Sagittarius A star, the scrambling time is milliseconds. The mathematical framework must describe information processing at this speed. The Margulis-Levitin theorem sets the maximum speed. Black holes operate at the maximum. The mathematical framework must describe dynamics at the absolute physical limit. The firewall paradox shows that the mathematical conflict extends beyond the singularity to the event horizon itself. The AMPS argument demonstrates that three mathematical principles, unitarity, the equivalence principle, and quantum field theory, are mathematically inconsistent at the horizon of an old black hole. The mathematical failure is not confined to the center, it extends to the boundary. The ER equals EPR conjecture proposes a mathematical identification between entanglement and wormholes. If correct, this identification would merge two previously separate mathematical frameworks, quantum information theory and general relativistic geometry, into a single unified framework. The mathematical failure might be resolved by this merger, which would provide a mathematical language rich enough to describe both quantum correlations and geometric structures simultaneously. Something is wrong with our mathematical assumptions about the nature of spacetime. The assumption of smoothness, the assumption of continuity, the assumption that spacetime can be described by a differentiable manifold with a well-defined metric at every point, must break down at the Planck scale. The mathematics that work so well at everyday scales, at astronomical scales, at the event horizon itself, fails at the singularity because the assumption on which it is built, the smoothness of spacetime, is no longer valid. But here is what makes this truly terrifying. The mathematical failure at the singularity is connected to the information paradox in a direct and unavoidable way. Stephen Hawking showed in 1974 that black holes emit thermal radiation. This Hawking radiation carries no information about what fell in. If the black hole evaporates completely, all information is lost. Unitarity is violated. The mathematical framework of quantum mechanics, which requires unitary evolution, is contradicted. The information paradox is a mathematical paradox in the deepest sense. It arises from the conflict between two mathematical frameworks, the differential geometry of general relativity, which produces the singularity, and the Hilbert space formalism of quantum mechanics, which requires unitarity. Both frameworks are mathematically consistent in their own domains. Both are extraordinarily successful in their own domains, and they produce contradictory predictions about what happens to information at the singularity. The no-hair theorem highlights the mathematical tension between exterior simplicity and interior complexity. The exterior is described by three numbers. The interior has 10 to the power of 77 microstates. The smooth manifold mathematics can describe the simple exterior perfectly. It cannot describe the complex interior. The mathematical failure at the singularity is connected to this gap. The three-number description is too simple to encode 10 to the power of 77 microstates. A richer mathematical framework is needed. The Strominger-Vafa counting of 1996 provided the first explicit microscopic accounting of the Bekenstein-Hawking entropy within string theory. For a specific class of extremal black holes, the number of string-theoretic microstates matches the macroscopic entropy formula exactly. This counting demonstrated that the microstates are real, that they can be counted, and that the mathematical framework of string theory has the capacity to describe them. The smooth manifold of general relativity cannot count these microstates. The string-theoretic framework can. The accretion disks around black holes provide observational evidence for the extreme conditions near the event horizon. X-ray spectroscopy reveals gravitationally redshifted emission lines from the inner disk. The redshift is consistent with emission from within a few Schwarzschild radii. The mathematical predictions of general relativity for the disk spectrum are confirmed. The mathematics works perfectly in the vicinity of the event horizon. It fails only at the center. Most physicists believe unitarity is preserved. Hawking conceded his bet with John Preskill in 2004. The island formula, developed in 2019 and 2020, showed that the entropy of Hawking radiation follows the Page curve, confirming unitary evolution within certain models. But the mechanism by which information escapes remains unclear. The mathematical description of the escape process requires a framework that combines general relativity and quantum mechanics in a way that no current mathematics can achieve. The Bekenstein-Hawking entropy provides a quantitative measure of the mathematical complexity hidden behind the event horizon. The entropy of a solar mass black hole is roughly 10 to the power of 77. This number represents the microscopic complexity of the black hole, the number of distinct mathematical states it can occupy while looking identical from the outside. The mathematical failure at the singularity is connected to this complexity. The smooth manifold mathematics cannot describe 10 to the power of 77 microstates. It can describe only the macroscopic properties: mass, charge, spin. The full microscopic description requires a mathematical framework that goes beyond smooth manifolds. The firewall paradox, introduced in 2012 by Almhiri, Marolf, Polchinski, and Sully, sharpened the mathematical conflict. The AMPS argument showed that three mathematical principles, unitarity, the equivalence principle, and the validity of quantum field theory, cannot all hold simultaneously at the event horizon of an old black hole. At most two can hold. This is a mathematical impossibility theorem, a proof that the three principles are mathematically inconsistent in the context of black hole evaporation. The ER equals EPR conjecture, proposed by Susskind and Maldacena in 2013, offers a resolution through a radical mathematical identification. It states that quantum entanglement and wormholes are the same mathematical object. Every pair of entangled particles is connected by a microscopic Einstein-Rosen bridge. This identification, if correct, would merge the mathematics of quantum information theory with the mathematics of general relativistic geometry, creating a unified mathematical framework in which the singularity might be resolved. The Penrose process and the thermodynamics of rotating black holes provide additional mathematical constraints. The four laws of black hole mechanics, established by Bardeen, Carter, and Hawking, mirror the four laws of thermodynamics. The Hawking temperature is inversely proportional to mass. The Bekenstein-Hawking entropy is proportional to area. Any mathematical framework that resolves the singularity must reproduce these thermodynamic relationships. The thermodynamics constrains the mathematics. The scrambling time, the time for the black hole to process infalling information and distribute it across the horizon, is milliseconds for Sagittarius A star. Patrick Hayden and John Preskill showed that black holes saturate the quantum bound on scrambling speed. The mathematical framework that describes this scrambling must be consistent with the thermodynamics, with unitarity, and with the geometry of the event horizon. These constraints are so tight that they significantly narrow the space of possible mathematical frameworks for quantum gravity. The connection between the mathematical failure and the arrow of time is deep. The second law of thermodynamics, which says entropy never decreases, gives time its direction. The mathematical framework of general relativity is time-symmetric. The equations work equally well forward and backward in time, but the singularity breaks this symmetry. The singularity at the center of a black hole is in the future, not the past. It is a final state, not an initial state. The mathematical failure has a temporal orientation. The mathematics fails in the future, at the end point of the collapse, not in the past. The Weyl curvature hypothesis connects this temporal orientation to the mathematical structure of the singularity. Penrose proposed that the initial singularity of cosmological models has low Weyl curvature, while black hole singularities have high Weyl curvature. The mathematical structure of the singularity encodes the arrow of time. The mathematical failure at the singularity is not just a failure of the equations, it is a failure that carries temporal information, pointing in the direction of increasing entropy, in the direction of the future. The Penrose process and the ergosphere reveal that the mathematical framework of general relativity describes black holes as dynamic thermodynamic systems. Energy can be extracted from rotating black holes through the ergosphere. The extraction obeys specific mathematical relationships. The four laws of black hole mechanics are mathematical consequences of the field equations. These laws must be reproduced by any mathematical framework that resolves the singularity. The scrambling time for Sagittarius A star is on the order of milliseconds. The Hayden-Preskill protocol shows that individual quantum bits can be recovered from the Hawking radiation after one scrambling time. The mathematical framework must describe this recovery. It must be consistent with unitarity, with thermodynamics, and with the geometry. These constraints are severe and mutually reinforcing. The mathematical failure is connected to the concept of curvature invariants, quantities that measure the curvature of spacetime in a coordinate-independent way. The simplest curvature invariant is the Kretschmer scalar, formed from the contraction of the Riemann tensor with itself. For a Schwarzschild black hole, the Kretschmer scalar is proportional to the mass squared divided by the radial distance to the sixth power. As the radial distance approaches zero, the Kretschmer scalar diverges. This divergence is present in every coordinate system. It is a genuine mathematical infinity, a coordinate-independent statement that the curvature is infinite at the center. Other curvature invariants diverge as well. The Ricci scalar, the contraction of the Ricci tensor, diverges for singularities in the presence of matter. The Weil tensor, which measures the tidal component of curvature, diverges. Every mathematical measure of curvature that can be constructed from the Riemann tensor diverges at the singularity. The mathematical failure is total and universal. The relationship between curvature invariants and physical observables is direct. Tidal forces, which stretch and compress physical objects, are proportional to components of the Riemann tensor. The divergence of the Riemann tensor at the singularity means the tidal forces are infinite. The mathematical statement of infinite curvature corresponds to the physical statement of infinite tidal force. The mathematical failure has physical consequences. The prediction that any physical object approaching the singularity will be stretched and compressed by infinite forces. This prediction is clearly unphysical. Infinite forces do not exist in nature. The mathematical infinity is a signal that the mathematical framework has been pushed beyond its domain of validity. At some point before the curvature reaches infinity, quantum gravitational effects must modify the equations, replacing the divergence with a finite maximum. The Planck curvature, the curvature at which quantum gravitational effects dominate, is the natural candidate for this maximum. The curvature reaches the Planck curvature and then stops increasing, halted by quantum effects that the classical mathematics ignores. The concept of geodesic incompleteness is the technical definition of the mathematical failure. Geodesics, the mathematical paths through spacetime, terminate, after finite, proper time, at the singularity. The smooth manifold has a boundary. The mathematical description cannot be extended beyond it. The Penrose-Hawking theorems prove that this incompleteness is unavoidable within the smooth manifold framework. The mathematical failure is guaranteed by the mathematical structure of the theory. The Kruskal-Sekerez coordinates reveal the maximal analytic extension of the Schwarzschild spacetime. Even in this maximal extension, the singularity persists. The smooth manifold has reached its mathematical limit. The mathematics cannot go further. The singularity is the mathematical wall at the end of the road. The mathematical failure at the singularity is hidden behind the event horizon. We cannot observe it, we cannot probe it, we cannot test our proposed replacements directly. The universe has placed the most profound mathematical failure in all of physics behind an impenetrable barrier, visible only to those who fall through and forfeit the ability to report their findings. The failure of mathematics inside black holes is the most important unsolved problem in physics, and it is permanently shielded from direct observation. The event horizon ensures that no experiment conducted inside the black hole can communicate its results to the outside. The mathematical failure is the most important phenomenon that can never be directly observed. It must be understood through theory alone, constrained by the twin pillars of general relativity and quantum mechanics, guided by the information paradox, the holographic principle, and the thermodynamics of black holes. The relationship between the mathematical failure and the concept of determinism is also important. If the mathematics fails at the singularity, the future cannot be predicted from the present. Determinism breaks down. The equations that would determine the future have produced infinity and can no longer function. The mathematical failure is a failure of predictability, a failure of the most basic requirement of physics, that the laws of nature determine what happens next. If the singularity is resolved by quantum gravity, determinism is restored, at least in the quantum mechanical sense. The quantum state evolves unitarily. The present uniquely determines the future. The mathematical framework of quantum gravity produces finite predictions at all times. The failure of determinism at the singularity is an artifact of the classical mathematical framework, not a genuine physical feature. The mathematical failure at the singularity has motivated the most ambitious program in the history of theoretical physics, the search for a mathematical framework that does not fail. This program, the search for quantum gravity, has produced a landscape of proposals, each offering a different mathematical language for describing the center of a black hole. Each proposal replaces the smooth manifold of general relativity with something else, something that can accommodate the extreme conditions at the singularity without producing infinity. The first proposal is string theory. String theory replaces point particles with one-dimensional vibrating strings, roughly the Planck length in size. The mathematical framework is dramatically different from the differential geometry of general relativity. Instead of smooth manifolds, string theory operates on string world sheets, two-dimensional surfaces swept out by strings as they propagate through spacetime. The mathematical tools are conformal field theory, algebraic geometry, and the theory of moduli spaces. In string theory, the mathematical failure at the singularity is resolved because strings have a minimum size. A point particle can be compressed to zero size, and the mathematical description diverges. A string cannot be compressed below its fundamental length. The mathematics that describes the string remains well defined at all scales, because the finite size of the string prevents the divergence. The mathematical failure of general relativity is replaced by the mathematical success of string theory, at least in principle. The fuzzball program, developed by Samir Mathur and collaborators, provides the most explicit string theoretic resolution. The entire classical interior, including the singularity, is replaced by a complicated structure of strings and branes. The smooth manifold is replaced by a fuzzy, quantum gravitational structure. The mathematical language is no longer differential geometry but string theory's algebraic and topological toolkit. The infinity at the center is replaced by a finite, complicated, but mathematically well-defined configuration. For certain simplified black holes, the fuzzball construction is explicit and complete. The number of fuzzball microstates matches the Bekenstein-Hawking entropy exactly. For a solar mass black hole, this is 10 to the power of 77 distinct configurations, each a different mathematical object, each well-defined, each finite. The mathematical failure has been replaced by mathematical richness. But the fuzzball program has limitations. Explicit constructions exist only for idealized cases with high symmetry. Extending the construction to realistic astrophysical black holes remains open. The mathematical complexity of the fuzzball geometries is enormous, and many technical challenges remain. The second proposal is loop quantum gravity. Instead of replacing point particles with strings, loop quantum gravity replaces the smooth manifold of general relativity with a discrete quantum geometry. Space is not continuous, but is composed of discrete quanta, finite-sized chunks of geometry connected by spin network edges. The mathematical framework is based on the representation theory of the gauge group of general relativity, using tools from knot theory and spin foam models. In loop quantum gravity, the mathematical failure at the singularity is resolved by discreteness. The smooth manifold assumption, which is the root of the mathematical failure, is replaced by a discrete structure that has a minimum volume, a minimum area, and a minimum curvature. The density cannot reach infinity because the volume cannot reach zero. The mathematics remains well-defined at all scales because the discreteness prevents the divergence. The quantum bounce prediction of loop quantum gravity is a specific consequence of this discreteness. When matter collapses to the Planck density, the discrete quantum geometry generates a repulsive pressure that halts the collapse. The matter bounces. The singularity is replaced by a region of maximum but finite density. The mathematics that broke in general relativity remains unbroken in loop quantum gravity. The Planck star, proposed by Carlo Rovelli and Francesca Vidotto, provides a concrete picture. The singularity is replaced by a compact object at the Planck density. The mathematical description is finite, well-defined, and physically meaningful. The infinite density is replaced by the Planck density. The zero volume is replaced by the Planck volume. The mathematical failure is replaced by mathematical success at the Planck scale. The third proposal comes from the holographic principle and adds CFT. The mathematical framework here is radically different from both general relativity and loop quantum gravity. Instead of describing the three-dimensional interior of the black hole directly, the holographic approach describes it indirectly, through a two-dimensional quantum field theory on the boundary. Juan Maldacina's 1997 discovery of the AD-CFT correspondence showed that a theory of gravity in the bulk of anti-de Sitter space is mathematically equivalent to a quantum field theory on the bulk boundary. The boundary theory is well-defined, finite, and free of singularities. It uses the mathematical framework of quantum field theory, which is well understood and well tested. The mathematical failure at the singularity in the bulk corresponds to something smooth and finite in the boundary theory. The failure is an artifact of the bulk mathematical language, not a feature of the fundamental mathematics. The holographic principle suggests that the correct mathematical language for describing the interior of a black hole is not the three-dimensional differential geometry of general relativity but the two-dimensional quantum field theory of the boundary. The three-dimensional description is derived, secondary, approximate. The two-dimensional description is fundamental, primary, exact. The mathematical failure occurs in the derived description, not in the fundamental one. The numbers are striking. Maldacina's paper has been cited tens of thousands of times. Within ADS, CFT, the Bekenstein-Hawking entropy is exactly the logarithm of the number of boundary microstates. Information is preserved because the boundary theory is unitary. The page curve is reproduced by the island formula. The mathematical consistency of the boundary theory guarantees the resolution of the singularity in the bulk. The fourth proposal involves quantum error correction and emergent spacetime. Research by Daniel Harlow, Fernando Pastovsky, Benny Yoshida, John Preskill, and others revealed that the holographic encoding of spacetime has the mathematical structure of a quantum error-correcting code. The three-dimensional bulk geometry is encoded in the two-dimensional boundary through a redundant, error-resistant mathematical mapping. In this framework, the mathematical failure at the singularity is a failure of the error-correcting code. Away from the singularity, the code is robust, and the geometric description is reliable. Near the singularity, the code degrades. At the singularity, it has broken down completely. The mathematical description of the geometry, which is generated by the code, fails because the code fails. The failure is not in the mathematics of the boundary theory, which continues to work perfectly. It is in the mathematical translation from boundary to bulk, the translation that generates the geometric description. The fifth proposal is the gravitational path integral with replica wormholes. Recent work by Jeffrey Pennington, Ahmed Almieri, Thomas Hartmann, Juan Maldacina, and others showed that the gravitational path integral, when properly computed, includes contributions from exotic spacetime geometries called replica wormholes. These contributions, invisible in the semi-classical approximation, restore unitarity, reproduce the page curve, and ensure that the mathematical framework produces finite, consistent answers even in situations where the classical theory produces infinity. The replica wormholes are saddle points of the path integral that connect different copies of the spacetime. They are mathematical objects that have no classical counterpart. They exist only in the quantum theory. Their contribution is essential for mathematical consistency. Without them, the mathematics fails, producing the wrong entropy, the wrong page curve, the wrong answer. With them, the mathematics succeeds, producing the correct, unitary, information-preserving result. The sixth proposal is causal set theory, developed by Raphael Sorkin and others. Causal set theory replaces the smooth manifold of general relativity with a discrete set of spacetime events connected by causal relations. The mathematical framework is combinatorics and order theory rather than differential geometry. In a discrete spacetime, the point-like singularity cannot form. The mathematical failure is avoided because the mathematical framework does not permit the conditions under which the failure occurs. The seventh proposal is asymptotically safe gravity, initiated by Steven Weinberg in 1979. This approach does not replace the smooth manifold, but modifies the behavior of gravity at high energies. The gravitational coupling, instead of growing without bound, approaches a finite fixed point. The mathematical divergences are tamed. The infinite quantities become finite. The mathematical framework remains the same, differential geometry on smooth manifolds, but the behavior of the equations at extreme scales is modified. The computational complexity perspective, developed by Leonard Susskind and others, adds a dynamical dimension. The interior of a black hole grows over time because the quantum computational complexity of the state increases. The mathematical description of the interior, which uses the language of smooth geometry, eventually fails because the complexity exceeds the descriptive capacity of geometry. The mathematics fails not because the geometry becomes singular, but because the quantum state becomes too complex for any geometric description to capture. The convergence of all these proposals is remarkable. Every approach, from every direction, using every mathematical framework, arrives at the same conclusion. The mathematical failure at the singularity is not a feature of nature. It is a feature of the mathematical language we have been using to describe nature. The smooth manifold of general relativity is not the correct mathematical description of spacetime at the Planck scale. The correct description is different. Strings, or loops, or boundary fields, or causal sets, or a safe gravitational coupling. The details differ, but the conclusion is universal. The mathematics that fails is the wrong mathematics. The math is striking. Every approach identifies the Planck scale as the boundary between the valid and the invalid mathematical descriptions. Below the Planck density, the smooth manifold mathematics works perfectly. Above it, the smooth manifold mathematics fails and must be replaced by something else. The Planck scale is the frontier of mathematical validity. The convergence of independent mathematical approaches provides the strongest evidence about the resolution of the failure. String theory, loop quantum gravity, holographic duality, causal set theory, asymptotic safety, the gravitational path integral, all arrive at the same mathematical conclusion. The smooth manifold description fails at the Planck scale. The infinity at the singularity is an artifact of the smooth manifold assumption. The correct mathematics, whatever it turns out to be, produces finite answers. The Planck scale is the mathematical frontier. Below the Planck density, the smooth manifold mathematics works perfectly. Above it, the smooth manifold mathematics fails. The Planck length, roughly 10 to the power of negative 35 meters, is the scale at which the smooth manifold assumption breaks down. The Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, is the density at which the failure occurs. These are the natural scales of quantum gravity, formed from the three fundamental constants: Newton's gravitational constant, the speed of light, and Planck's reduced constant. The gap between the Planck scale and our experimental capabilities is roughly 17 orders of magnitude. The smallest distances probed by the Large Hadron Collider are roughly 10 to the power of negative 18 meters. The Planck length is roughly 10 to the power of negative 35 meters. No foreseeable accelerator can bridge this gap. The mathematical framework that resolves the singularity cannot be tested directly. It must be validated through mathematical consistency, through the constraints of the information paradox and black hole thermodynamics, and through indirect observational evidence. The observational constraints are tightening. Each gravitational wave detection tests general relativity in the strong field regime. Each event horizon telescope image constrains the near-horizon geometry. Future detectors, both ground-based and space-based, will push sensitivity further. The space-based detector LISA will detect supermassive black hole mergers. The ring-down signals from these mergers test the no-hair theorem. Any deviation from the predictions would signal new mathematics at or near the event horizon. The mathematical tools developed for the singularity problem have found applications across science: quantum error correction for quantum computing, holographic methods for strongly coupled physics, scrambling dynamics for quantum simulation, random quantum circuits for benchmarking. Each application was driven by the mathematical failure at the singularity. The most abstract mathematical problem in physics has generated practical tools with real-world applications. The connection between the mathematical failure and the nature of spacetime is the deepest implication. If the smooth manifold description fails at the Planck scale, then spacetime is not fundamentally smooth. It is smooth at everyday scales, as an approximation, but not at the Planck scale. The smoothness is emergent. The fundamental mathematical description is something else: discrete, holographic, informational, computational. The mathematical failure reveals the emergent nature of spacetime. The connection between the mathematical failure and the holographic principle deserves detailed examination. The Bekenstein-Hawking entropy, proportional to the horizon area, tells us that the information content of a black hole scales with area, not volume. This is a mathematical statement that the three-dimensional description is derived from a two-dimensional one. The fundamental mathematics is two-dimensional. The three-dimensional mathematics, including its singularity, is secondary. The island formula showed that the entropy of Hawking radiation follows the Page curve. The calculation involves quantum extremal surfaces and quantum extremal islands. These mathematical objects, which have no classical counterpart, are essential for reproducing the correct, unitary answer. Without them, the mathematics gives the wrong answer. The Hawking answer, information loss. With them, the mathematics gives the correct answer, the Page answer, information preservation. The mathematical framework that resolves the failure includes mathematical objects that are invisible in the classical theory. The replica wormholes are another example of mathematical objects that exist only in the quantum theory and that are essential for mathematical consistency. They are saddle points of the gravitational path integral that connect different copies of the spacetime. Their contribution ensures unitarity. Without them, the path integral gives the wrong answer. With them, it gives the correct answer. The mathematical resolution of the failure requires mathematical objects that the classical theory cannot see. The error-correcting structure of holographic spacetime provides the most explicit mechanism. The bulk geometry is encoded in the boundary through a quantum error-correcting code. The mathematical structure of this code determines how the bulk geometry is reconstructed from the boundary data. Near the singularity, the code degrades. The reconstruction fails. The geometric description breaks down, but the boundary data, the fundamental mathematical description, remains well defined. The failure is in the mathematical translation, not in the fundamental mathematics. The computational complexity perspective adds temporal depth. The interior of a black hole grows because the quantum complexity increases. Susskind proposed that the growth of the interior volume corresponds to the growth of computational complexity. The singularity is the point where the complexity exceeds the descriptive capacity of geometry. The mathematics of smooth manifolds can represent only a bounded amount of complexity. At the singularity, this bound is exceeded. The mathematics fails because the computation has outgrown the representation. The thermodynamic constraints from the Bekenstein-Hawking entropy, the Hawking temperature, and the four laws of black hole mechanics provide independent mathematical checks. Any mathematical framework that resolves the singularity must reproduce these thermodynamic properties. The exterior has finite, well-defined temperature and entropy. The interior must be compatible. A singularity with infinite density and undefined thermodynamics is incompatible with the finite exterior thermodynamics. The observational constraints from gravitational wave astronomy are tightening. Each detection tests general relativity. The ring-down signals test the no-hair theorem. Future detectors may reveal echoes or anomalies. The Event Horizon Telescope may resolve the photon ring. Each observation constrains the mathematical framework needed to describe the interior. The constraints from gravitational wave astronomy, from the Event Horizon Telescope, from the holographic principle, from the information paradox, from black hole thermodynamics, all converge on the same conclusion. The smooth manifold mathematics fails at the Planck scale and must be replaced. The mathematical concept of universality provides perspective. In condensed matter physics, universality refers to the phenomenon in which diverse microscopic systems exhibit the same macroscopic behavior. The details of the microscopic physics do not matter for the macroscopic description. Similarly, the diverse proposals for quantum gravity may exhibit universality at the macroscopic level. String theory, loop quantum gravity, holographic duality, and other approaches may all produce the same macroscopic predictions for the resolution of the singularity, even though their microscopic mathematical frameworks differ. The concept of asymptotic safety illustrates how the mathematical framework of smooth manifolds might be preserved, with modifications, at the Planck scale. In asymptotically safe gravity, the gravitational coupling approaches a finite fixed point at high energies. The smooth manifold mathematics is retained, but the behavior of the equations is modified. The infinite quantities become finite. The mathematical framework is the same, but its extreme behavior is tamed. Whether the correct mathematical framework preserves smooth manifolds with modifications or replaces them entirely is one of the central open questions. String theory replaces them. Loop quantum gravity replaces them. Causal set theory replaces them. Asymptotic safety modifies them. The mathematical evidence is not yet sufficient to decide between these options. The Penrose-Hawking singularity theorems deserve particular attention in the context of the mathematical failure. The theorems prove that singularities are unavoidable under very general mathematical conditions. The proofs are topological, using mathematical techniques from algebraic topology. They do not depend on the specific details of the matter or the symmetry of the collapse. They depend only on the mathematical structure of the field equations, the positivity of energy, and the existence of a trapped surface. The generality of the theorems is both their strength and their limitation. The strength is that they prove the mathematical failure is unavoidable within the framework of general relativity. No matter how you set up the problem, the mathematics will fail. The limitation is that the theorems say nothing about what happens when the framework is extended. If the mathematical framework is changed, if smooth manifolds are replaced by discrete structures or holographic encodings, the theorems no longer apply. The mathematical failure guaranteed by the theorems is guaranteed only within the smooth manifold framework. Change the framework, and the guarantee evaporates. Every candidate for quantum gravity changes the framework. String theory replaces point particles with strings. Loop quantum gravity replaces smooth manifolds with discrete quantum geometry. Causal set theory replaces continuous spacetime with discrete causal elements. Each change evades the singularity theorems by modifying the mathematical assumptions on which the theorems rest. The theorems guarantee the failure within the old framework. The new framework, whatever it turns out to be, will avoid the failure by operating on different mathematical foundations. The Planck star of loop quantum gravity provides a concrete mathematical example. The singularity theorems require positive energy density. At the Planck density, the quantum geometry generates effective contributions to the energy density that violate the positive energy condition. The mathematical condition on which the theorem rests is violated by the quantum effects. The theorem no longer applies. The singularity does not form. The mathematics succeeds where it previously failed. The holographic approach evades the theorems differently. The boundary theory, which is the fundamental description, lives on a manifold without a singularity. The bulk singularity is a feature of the derived geometric description. The theorems apply to the derived description but not to the fundamental one. The mathematical failure is in the projection, not in the reality. The connection between the mathematical failure and the concept of emergence is one of the deepest implications. If spacetime is emergent, arising from more fundamental quantum degrees of freedom, then the smooth manifold of general relativity is an approximate mathematical description, valid at scales much larger than the Planck scale. At the Planck scale, the approximation breaks down. The smooth manifold develops a singularity, but the underlying quantum description from which the smooth manifold emerges remains well defined. The analogy with temperature is instructive. Temperature is an emergent quantity arising from the collective motion of molecules. It is well defined for large collections of molecules. It becomes meaningless at the level of individual molecules. The concept of temperature fails at the molecular scale, not because reality fails, but because the concept is an approximation that is valid only at macroscopic scales. Similarly, the smooth manifold of general relativity is an emergent concept, valid at scales larger than the Planck scale. At the Planck scale, the concept fails. The smooth manifold develops a singularity. But reality does not fail. The underlying quantum degrees of freedom continue to evolve normally. The mathematical failure is a failure of the emergent concept, not of reality. So, the observational constraints continue to tighten. Roughly 90 gravitational wave events have been detected. Each tests general relativity in the strong field regime. Future detectors, including the Einstein Telescope, Cosmic Explorer, and LISA, will push sensitivity further. The photon ring may be resolved by future Event Horizon Telescope observations. Each observation constrains the mathematical framework needed to describe the interior. The constraints from gravitational wave astronomy, from the Event Horizon Telescope, from the holographic principle, from the information paradox, from black hole thermodynamics, all converge on the same conclusion. The smooth manifold mathematics fails at the Planck scale and must be replaced. The mathematical concept of universality provides perspective. In condensed matter physics, universality refers to the phenomenon in which diverse microscopic systems exhibit the same macroscopic behavior. The details of the microscopic physics do not matter for the macroscopic description. Similarly, the diverse proposals for quantum gravity may exhibit universality at the macroscopic level. String theory, loop quantum gravity, holographic duality, and other approaches may all produce the same macroscopic predictions for the resolution of the singularity, even though their microscopic mathematical frameworks differ. The concept of asymptotic safety illustrates how the mathematical framework of smooth manifolds might be preserved with modifications at the Planck scale. In asymptotically safe gravity, the gravitational coupling approaches a finite fixed point at high energies. The smooth manifold mathematics is retained, but the behavior of the equations is modified. The infinite quantities become finite. The mathematical framework is the same, but its extreme behavior is tamed. Whether the correct mathematical framework preserves smooth manifolds with modifications or replaces them entirely is one of the central open questions. String theory replaces them. Loop quantum gravity replaces them. Causal set theory replaces them. Asymptotic safety modifies them. The mathematical evidence is not yet sufficient to decide between these options. And this is where the answer becomes deeply unsettling, because the mathematical failure at the singularity is not just a technical problem to be solved by finding better equations. It is a conceptual problem that challenges our understanding of what mathematics is and what its relationship to physical reality is. If the mathematics of smooth manifolds fails at the singularity, what does this tell us about the nature of spacetime, about the nature of mathematics, about the nature of reality itself? The Bekenstein-Hawking entropy formula provides the most powerful constraint on the resolution of the mathematical failure. The entropy of a solar mass black hole is roughly 10 to the power of 77. This number constrains the mathematical framework. Any framework that resolves the singularity must accommodate this number of microstates. The smooth manifold mathematics cannot. The framework that replaces it must. End. The holographic principle states that the fundamental mathematical description is two-dimensional. The three-dimensional bulk is derived. The mathematical failure occurs in the derived description. The fundamental description is well defined. This is the most important insight about the nature of the failure. Mark van Ramsdonk showed that entanglement generates spacetime. Reducing entanglement causes spacetime to disconnect. The mathematical structure of the bulk is generated by the entanglement of the boundary. At the Singularity, the entanglement structure has been disrupted beyond the capacity of the geometric output to remain smooth. The mathematical failure is a failure of the output, not of the input. The error-correcting structure of holographic spacetime, discovered by Harlow and collaborators, provides the mechanism. The bulk is encoded in the boundary through a quantum error-correcting code. Near the Singularity, the code degrades. At the Singularity, it fails. The mathematical failure is a failure of the code, not of the underlying quantum state. The Wheeler-DeWitt equation has no time variable. The quantum state is static. Time is reconstructed from correlations. The smooth manifold mathematics treats time as fundamental. If time is emergent, the smooth manifold is using the wrong mathematical starting point. The failure at the Singularity is a consequence of this wrong starting point. The computational complexity perspective adds dynamics. The interior grows because complexity increases. The Singularity is where complexity exceeds geometric capacity. The mathematical failure is a capacity limit of the geometric language. The scrambling time for Sagittarius A* is milliseconds. The Margulis-Levitin theorem sets the maximum processing speed. Black holes operate at this maximum. The mathematical framework must describe processing at the physical limit. The Page curve is the mathematical signature of information preservation. Rising entropy in the first half, falling entropy in the second half. The island formula reproduces this curve. Quantum extremal islands grow during evaporation, transferring information from the failing bulk description to the well-defined boundary description. The Planck star replaces the Singularity with a compact object at the Planck density. The mathematics is well defined. Finite density, finite volume, finite curvature. The mathematical failure is replaced by mathematical success at the Planck scale. The arrow of time points toward the Singularity. The Weyl curvature hypothesis connects the mathematical structure of the Singularity to the thermodynamic arrow. The failure has temporal orientation. It occurs in the future direction. The deeper truth about why mathematics fails inside black holes is that the failure reveals something profound about the nature of the relationship between mathematics and physical reality. The failure is not a bug. It is a feature. It is the universe telling us, with mathematical precision, that the mathematical language we have been using is not the right language for the domain we are trying to describe. Throughout the history of physics, mathematical failures have been the most productive signals of progress. The ultraviolet catastrophe of classical electromagnetism, the prediction that hot objects should radiate infinite energy at short wavelengths, was a mathematical failure that led to quantum mechanics. The divergence of the Abraham-Lorentz equation for the self-force of a charged particle was a mathematical failure that led to quantum electrodynamics. The non-renormalizability of the Fermi theory of weak interactions was a mathematical failure that led to the electroweak theory. In each case, the failure was not a dead end but a signpost, pointing toward a deeper mathematical framework that resolved the failure and revealed new physics. The mathematical failure at the Singularity of a black hole is the latest and deepest such signpost. It points toward quantum gravity, a mathematical framework that we do not yet possess in its complete form. But the direction is clear. The failure tells us that the mathematical assumption of smooth, continuous spacetime must be abandoned at the Planck scale. Something else must take its place. And whatever takes its place will constitute the most profound change in the mathematical description of nature since the introduction of quantum mechanics. Let that sink in. The assumption that spacetime is a smooth manifold has been the foundation of physics since the development of calculus in the 17th century. Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, all are built on the assumption that space and time are smooth, continuous, differentiable. The mathematical tools of calculus, differential equations, partial differential equations, tensor analysis, all presuppose this smoothness. The failure at the Singularity tells us that this assumption, which has served physics for more than 3 centuries, is not exactly right. Space-time is smooth at everyday scales. It is smooth at astronomical scales. It is smooth at the event horizon. But at the Planck scale, it is not smooth. It is something else. And the mathematics that describes that something else will be fundamentally different from the mathematics that has served physics for the past 300 years. The holographic principle provides the most concrete evidence for this radical change. If the 3-dimensional bulk spacetime is a mathematical projection of 2-dimensional boundary physics, then the 3-dimensional smooth manifold is not the fundamental mathematical object. The fundamental object is the 2-dimensional boundary quantum state, described by the mathematics of quantum field theory and quantum information theory. The 3-dimensional geometry, including its singularity, is a derived mathematical construct emerging from the boundary through a holographic encoding. Mark van Ramsdonk showed in 2010 that the mathematical structure of the bulk geometry is generated by the entanglement structure of the boundary state. If you reduce the entanglement, the geometry disconnects. The smoothness of spacetime is not a given mathematical input. It is a mathematical output generated by entanglement. At the singularity, where the entanglement structure has become too disrupted to generate a smooth geometry, the mathematical output fails. But the mathematical input, the boundary quantum state, continues to evolve smoothly and unitarily. The error-correcting structure, discovered by Harlow and collaborators, provides the mathematical mechanism. The bulk geometry is encoded in the boundary through a quantum error-correcting code. The code has a specific mathematical structure that determines how the bulk geometry is reconstructed from the boundary data. Near the singularity, the code degrades. The reconstruction fails. The geometry develops a singularity not because the boundary state has a singularity, but because the mathematical translation from boundary to bulk breaks down at extreme curvatures. This perspective transforms our understanding of the mathematical failure. The failure is not in the mathematics. The mathematics of the boundary theory is perfectly well defined at all times. The failure is in the translation, in the holographic map from boundary to bulk, in the mathematical procedure that generates the 3-dimensional geometry from the 2-dimensional quantum state. The failure is in the dictionary, not in the language. Let that sink in. The Wheeler-DeWitt equation, one of the earliest attempts at quantum gravity, illustrates another aspect of the mathematical failure. The equation, which describes the quantum state of the universe, has no time variable. Time, in this formulation, is not a mathematical input, but must be reconstructed from the quantum state. The mathematical framework of quantum gravity may not have time as a fundamental variable. If time is not fundamental, then the smooth manifold of general relativity, which treats time as a fundamental coordinate, is using the wrong mathematical language. The failure at the singularity is a consequence of using a mathematical framework that treats time as fundamental when time is actually emergent. The computational complexity perspective adds yet another layer. Susskind's proposal that the interior volume grows with quantum complexity suggests that the mathematical failure at the singularity is a computational failure. The quantum state has become so complex that no geometric description can represent it. The mathematics of smooth manifolds has a finite descriptive capacity, a finite ability to encode quantum information. At the singularity, this capacity is exceeded. The mathematics fails because the computation has outgrown the representation. The deeper truth, then, is this. Mathematics fails inside black holes because we have been using the wrong mathematical language. The language of smooth, continuous, differentiable manifolds, the language that has served physics so brilliantly for 3 centuries, is not the language of nature at the Planck scale. At the Planck scale, nature speaks a different mathematical language, a language of discrete quantum geometry, or of boundary quantum fields, or of quantum information and entanglement, or of causal sets, or of something we have not yet imagined. The singularity is the point where the old language runs out of words and the new language must be spoken. This is not science fiction. This is the direction in which mainstream theoretical physics is moving, driven by rigorous mathematical results within the ADS CFT framework. by the connection between entanglement and geometry, by the error-correcting structure of holographic spacetime, and by the computational complexity dynamics of black hole interiors, the mathematical failure at the singularity is not a permanent obstacle. It is a temporary barrier, soon to be overcome by a new mathematical framework that speaks the language of nature at the Planck scale. What does it mean that mathematics fails inside black holes? What does it mean for our understanding of the relationship between mathematics and nature? What does it mean for the future of physics? It means, first and most directly, that we are at a frontier, not a geographical frontier, not an observational frontier, but a mathematical frontier. The edge of what our current mathematical language can describe, the boundary beyond which new mathematical tools are needed, the frontier where the most fundamental questions about the nature of reality await answers that we do not yet have the mathematical vocabulary to express. The history of physics is a history of mathematical frontiers crossed. Newton crossed the frontier from geometry to calculus, and classical mechanics was born. Maxwell crossed the frontier from scalar fields to vector fields, and electromagnetism was unified. Einstein crossed the frontier from flat geometry to curved geometry, and general relativity was born. Dirac crossed the frontier from ordinary quantum mechanics to relativistic quantum mechanics, and the positron was predicted. Each crossing required a new mathematical language, a new set of tools, a new way of expressing the relationships between physical quantities. The singularity is the next frontier. Crossing it requires a mathematical language that does not yet exist in its complete form. The candidates, strings, loops, holographic fields, causal sets are partial versions of this language, each capturing some aspect of the truth. The complete language, the language of quantum gravity, will be the most profound mathematical achievement in the history of science. There is a philosophical pause required here. The mathematical failure at the singularity challenges one of the deepest assumptions of the scientific enterprise, that nature is mathematical. The Pythagorean idea that the universe is built from numbers, the Galilean idea that the book of nature is written in the language of mathematics, the Wagnerian observation that mathematics is unreasonably effective in describing the physical world, all of these assume that mathematics and nature are in perfect correspondence. The singularity is a point where this correspondence breaks. Nature continues. Mathematics does not. The universe does not produce infinity at the center of a black hole. Our mathematical description does. This suggests that mathematics is not the language of nature in any absolute sense. It is a language, among potentially many, that nature speaks at certain scales and in certain domains. At everyday scales, the language of calculus and differential equations is spoken fluently by nature. At atomic scales, the language of linear algebra and Hilbert spaces is spoken. At the Planck scale, nature speaks a different language, one we are still learning. The practical implications of the mathematical failure have been substantial. The attempt to resolve the failure has driven the development of string theory, loop quantum gravity, the holographic principle, quantum error correction, quantum information theory, computational complexity theory, and gravitational wave astronomy. Each of these represents a major advance, and each was motivated by the need to find mathematics that works where the current mathematics fails. The observational landscape continues to evolve. The LIGO-Virgo-Kagra collaboration has detected roughly 90 gravitational wave events. The Event Horizon Telescope has photographed 2 supermassive black holes. Future detectors will provide more precise measurements. Future observations may reveal subtle effects near the event horizon that constrain the mathematical framework needed to describe the interior. The mathematical tools developed for the singularity problem have found applications across science. Quantum error correction is essential for fault-tolerant quantum computing. The holographic correspondence has applications in condensed matter physics, nuclear physics, and fluid dynamics. The thermodynamics of black holes has illuminated the physics of strongly coupled quantum systems. The most abstract mathematical question in physics has generated practical tools with real-world impact. The study of the mathematical failure has driven advances across multiple fields. The holographic principle connected Riemannian geometry to quantum information theory. The ADS CFT correspondence connected hyperbolic geometry to conformal field theory. The error-correcting structure connected coding theory to differential geometry. Penrose's singularity theorem introduced topological methods to general relativity. Each connection was unexpected. Each enriched both fields. The mathematical failure at the singularity has been one of the most productive catalysts for mathematical innovation in the history of science. The practical applications continue to expand. Quantum error correction for fault-tolerant quantum computing. Tensor networks for machine learning and data science. Holographic methods for strongly coupled quantum systems. Gravitational wave data analysis, using matched filtering based on numerical relativity. Each application was driven, directly or indirectly, by the attempt to find mathematics that works where the current mathematics fails. The philosophical question of whether mathematics is discovered or invented takes on special significance at the singularity. If mathematics is discovered, if mathematical structures exist independently of human minds, then the mathematical language of quantum gravity already exists, waiting to be found. The singularity is a place where the discovered mathematics runs out, and new mathematics must be discovered. If mathematics is invented, if it is a human construction, then the mathematical failure at the singularity means we need to invent new constructions, new frameworks, new tools. Either way, the mathematical failure is temporary. Whether the correct mathematics is waiting to be discovered in the Platonic realm of mathematical forms or waiting to be invented by the creative ingenuity of human minds, it will be found. The history of physics guarantees it. Every mathematical failure has been resolved. The singularity will be resolved too. The next generation of physicists will inherit both the problem and the tools. Quantum computers may simulate aspects of quantum gravity. New mathematical frameworks may emerge from the intersection of physics and pure mathematics. The resolution of the mathematical failure at the singularity may come from an unexpected direction, from a connection that no one currently suspects, from a piece of mathematics that has not yet been invented. The failure of mathematics inside black holes is not the end of the story. It is the beginning of the search for the mathematical language that nature speaks at the Planck scale. The beginning of the deepest revolution in our understanding of the relationship between mathematics and reality. The connection between the mathematical failure and practical technology continues to strengthen. Quantum error correction, inspired by the holographic encoding of spacetime, is essential for building fault-tolerant quantum computers. The mathematical framework of tensor networks, which describes the holographic correspondence, has applications in machine learning, data compression, and quantum simulation. The thermodynamics of black holes has been applied to problems in condensed matter physics, providing mathematical tools for studying strongly coupled quantum systems. The study of the mathematical failure has also revealed unexpected connections between physics and pure mathematics. Penrose's singularity theorem introduced topological methods to general relativity. The holographic principle connected Riemannian geometry to quantum information theory. The ADS CFT correspondence connected hyperbolic geometry to conformal field theory. The error-correcting structure of spacetime connected algebraic coding theory to differential geometry. Each connection was unexpected. Each enriched both fields. The philosophical implications of the mathematical failure deserve careful consideration. If mathematics is the language of nature, and if that language fails at the singularity, then either nature has aspects that transcend mathematical description, or we are using the wrong mathematical language. Most physicists believe the latter. They believe that a better mathematical language exists, the language of quantum gravity, and that this language will describe the singularity without producing infinity. The failure is in our language, not in nature. This is an important distinction. Nature does not produce infinity at the center of a black hole. Nature produces whatever it produces, presumably something finite, something physical, something real. Our mathematical description produces infinity. The gap between what nature does and what our mathematics says nature does is the measure of our ignorance. The mathematical failure at the singularity is a measure of how far our current mathematical language is from the mathematical language of nature at the Planck scale. The study of the mathematical failure has driven advances across multiple fields. The holographic principle connected Riemannian geometry to quantum information theory. The ADS CFT correspondence connected hyperbolic geometry to conformal field theory. The error-correcting structure connected coding theory to differential geometry. Penrose's singularity theorem introduced topological methods to general relativity. Each connection was unexpected. Each enriched both fields. The mathematical failure at the singularity has been one of the most productive catalysts for mathematical innovation in the history of science. The practical applications continue to expand. Quantum error correction for fault-tolerant quantum computing, tensor networks for machine learning and data science, holographic methods for strongly coupled quantum systems, gravitational wave data analysis using matched filtering based on numerical relativity. Each application was driven, directly or indirectly, by the attempt to find mathematics that works where the current mathematics fails. The philosophical question of whether mathematics is discovered or invented takes on special significance at the singularity. If mathematics is discovered, if mathematical structures exist independently of human minds, then the mathematical language of quantum gravity already exists, waiting to be found. The singularity is a place where the discovered mathematics runs out, and new mathematics must be discovered. If mathematics is invented, if it is a human construction, then the mathematical failure at the singularity means we need to invent new constructions, new frameworks, new tools. Either way, the mathematical failure is temporary. Whether the correct mathematics is waiting to be discovered in the Platonic realm of mathematical forms, or waiting to be invented by the creative ingenuity of human minds, it will be found. The history of physics guarantees it. Every mathematical failure has been resolved. The singularity will be resolved too. The next generation of physicists will close this gap. They will have quantum computers capable of simulating quantum gravitational systems. They will have gravitational wave detectors of unprecedented sensitivity. They will have mathematical frameworks more refined than anything available today. And they will have the accumulated wisdom of 50 years of work on the singularity problem, pointing them toward the mathematical language that nature speaks at its most extreme. The resolution of the mathematical failure will have implications far beyond black hole physics. It will provide the mathematical language for describing the early universe, when densities may have approached or exceeded the Planck density. It will provide the mathematical tools for understanding the quantum structure of spacetime at all scales. It will connect gravity to the other forces through a unified mathematical framework. The mathematical failure has driven the most productive era of theoretical physics in recent history. The information paradox, the holographic principle, the ADS, CFT correspondence, the firewall paradox, the island formula, quantum error correction, computational complexity. Each was driven by the attempt to resolve the mathematical failure at the singularity. The failure has been the most productive failure in the history of science. The connection between the mathematical failure and the philosophy of mathematics is worth contemplating. The mathematical failure challenges the Platonic view that mathematical objects exist independently of physical reality. If the smooth manifold, a mathematical object of great beauty and elegance, fails to describe physical reality at the singularity, does the smooth manifold still exist as a mathematical object? Of course it does. But its relationship to physical reality is limited. It describes reality at some scales and fails at others. The mathematical object is eternal. Its physical relevance is bounded. The failure also challenges the instrumentalist view that mathematical theories are merely tools for prediction. If the tool fails, do we discard it? Not entirely. We continue to use it where it works, in the vast domain of everyday physics and astronomy. But we recognize that it has a boundary, a frontier beyond which it is no longer reliable. The mathematical failure at the singularity defines the frontier of general relativity's mathematical validity. The beginning of the theory of quantum gravity, the theory that will replace smooth manifolds with whatever nature actually uses at the Planck scale. The theory that will produce finite answers where the current mathematics produces infinity. The theory that will reveal the mathematical structure of reality at its deepest level. The theory that the singularity has been demanding, with silent mathematical patience, since Carl Schwarzschild first derived his solution on the Eastern Front in 1916. Mathematics has never failed before. In 3 centuries of physics, every phenomenon has yielded a finite, meaningful answer. The motion of planets, the behavior of atoms, the propagation of light, the structure of matter, the expansion of the universe, every question answered, every problem solved. And then the equations met the singularity, and they broke. The failure is not a flaw in mathematics. It is a message from nature, a message that says, you are using the wrong language. The language of smooth, continuous spacetime, the language that has served you so well for 300 years, is not my language at the smallest scales. At the Planck scale, at the center of every black hole, I speak a different language. A language of quantum geometry, of holographic encoding, of entanglement and information, of discrete causal structure. A language you are only beginning to learn. The mathematical failure at the singularity is the most important signal in the history of physics. Every previous signal of this kind, the ultraviolet catastrophe, the non-renormalizability of the Fermi theory, the divergence of classical electrodynamics, led to a revolution, quantum mechanics. The electroweak theory, quantum electrodynamics. Each revolution was triggered by a mathematical failure. Each failure was resolved by a new mathematical framework. Each new framework revealed physics that was previously invisible. The singularity will follow the same pattern. The mathematical failure will be resolved by a new framework, the framework of quantum gravity. And the new framework will reveal physics that is currently invisible, the quantum structure of spacetime, the informational basis of geometry, the computational dynamics of the universe at the Planck scale. General relativity describes the universe with extraordinary precision. It predicts gravitational waves, black hole shadows, orbital precession, gravitational lensing, time dilation, cosmological expansion. It is one of the great intellectual achievements of the human mind. And it contains, within its own equations, the proof of its own incompleteness. The singularity is the theory's confession that it cannot describe everything. That at one specific point, under one specific set of conditions, it fails. And the failure, far from diminishing the theory, ennobles it. The theory is honest. It tells us exactly where it breaks. It points, with mathematical precision, to the place where the next theory must begin. The next theory, quantum gravity, will be built on the ruins of the singularity. It will take the mathematical failure and transform it into mathematical success. It will replace the infinity with something finite. It will replace the breakdown with understanding. It will speak the language that nature speaks at the Planck scale. Somewhere, right now, the mathematics that will resolve the singularity is being developed. Perhaps it is a new formula being written on a whiteboard. Perhaps it is a new connection being glimpsed between two previously unrelated mathematical structures. Perhaps it is a new computational technique being tested on a quantum computer. The mathematics is out there, waiting to be discovered. The failure of mathematics inside black holes is temporary. The failure of human curiosity is not. And the failure of human ingenuity is not. The mathematical tools we will develop to resolve the singularity will be the most profound mathematical tools ever created. They will describe nature at the Planck scale, the most fundamental scale of physical reality. They will unify gravity and quantum mechanics. They will resolve the information paradox. They will preserve unitarity. They will reproduce the thermodynamics. And they will produce, at the center of every black hole, a finite, meaningful, physically interpretable answer where the current mathematics produces infinity. We will find the answer. We always have. Every mathematical failure in the history of physics has been resolved, often within a few decades, always to the profound enrichment of our understanding of nature. The singularity will be resolved too. And when it is, We will know what mathematics nature speaks at its most extreme, at its most fundamental, at its most beautiful. Every mathematical failure in the history of physics has been temporary. The ultraviolet catastrophe was resolved by quantum mechanics within a few years of its identification. The divergences of quantum electrodynamics were resolved by renormalization within 2 decades. The non-renormalizability of the Fermi theory was resolved by the electroweak theory within 15 years. Each failure was followed by a mathematical triumph that not only resolved the failure but revealed new physics that was previously invisible. The mathematical failure at the Singularity has lasted longer than any previous failure, more than a century since Schwarzschild's solution, more than 50 years since the information paradox. But the progress is real. The island formula reproduces the page curve. The holographic principle preserves information. The error-correcting code protects information from the Singularity. The convergence of independent approaches provides confidence. The answer is emerging. The mathematical language that will resolve the Singularity will be the most beautiful mathematics ever written. It will unify the discrete and the continuous, the geometric and the algebraic, the local and the global, the classical and the quantum. It will describe spacetime at the Planck scale with the same precision that calculus describes it at everyday scales. It will be the culmination of 3 centuries of mathematical physics and the beginning of a new era of understanding. The failure of mathematics inside black holes is the failure of one mathematical language. It is not the failure of mathematics itself. Mathematics is inexhaustible. Its resources are infinite. For every phenomenon that nature presents, mathematics contains a language capable of describing it. We have not yet found the language for the Singularity, but we will. We always have. The Singularity is the universe's most profound mathematical statement. It says, your language is not rich enough, your tools are not powerful enough, your framework is not deep enough. Find a better one. And physicists, driven by the mathematical failure, have been searching for that better framework for more than half a century. The search has produced some of the most beautiful mathematics ever written: string theory, loop quantum gravity, holographic duality, quantum error correction, computational complexity. Each is a partial glimpse of the mathematical language that nature speaks at the Planck scale. The complete language has not yet been found, but its contours are visible. It will be a language that combines the discrete and the continuous, that unifies the geometric and the algebraic, that connects the local and the global, that merges the classical and the quantum. It will be a language of unprecedented mathematical depth and beauty. The resolution is within reach. The theoretical tools are improving. The observational constraints are tightening. The convergence of independent approaches provides confidence. The island formula reproduces the page curve. The holographic principle preserves information. The error-correcting code protects information from the Singularity. The quantum bounce of loop quantum gravity replaces infinity with the Planck density. The fuzzballs of string theory replace the smooth interior with stringy structure. Every approach points in the same direction. The mathematics that fails is the wrong mathematics. The mathematics that succeeds is waiting to be discovered. The equations broke at the Singularity. They will not stay broken. The Bekenstein-Hawking entropy formula, S equals A over 4 in Planck units, is the mathematical Rosetta Stone, connecting gravity, thermodynamics, and quantum mechanics. It tells us that the information content of a black hole is proportional to its surface area, not its volume. If the information were distributed through the volume, the entropy would scale with volume. The fact that it scales with area tells us that the 3-dimensional mathematical description is derived from a 2-dimensional one. The fundamental mathematics is 2-dimensional. The 3-dimensional description, including its singularity, is a projection. The scrambling time provides a mathematical measure of the information processing speed inside the black hole. For Sagittarius A star, it is milliseconds. The Hayden-Preskel protocol shows that individual quantum bits can be recovered from the Hawking radiation after one scrambling time. The mathematical framework that describes this recovery must be consistent with the thermodynamics, with unitarity, and with the geometry. The constraints are severe. The mathematics is tightly determined. The page curve is the mathematical signature of information preservation. The entropy of the radiation rises during the first half of evaporation and falls during the second half. The island formula reproduces this curve through a gravitational calculation. The quantum extremal islands, regions of the interior that belong informationally to the radiation, provide the mathematical mechanism. The islands grow as the black hole evaporates, transferring information from interior to exterior. By the end, all information has been transferred. The connection between mathematical failure and consciousness is speculative but unavoidable. Consciousness, whatever it is, depends on information processing. Information processing depends on a well-defined mathematical description. If the mathematics fails at the singularity, can information processing continue? If it cannot, can consciousness persist? The mathematical failure at the singularity raises questions about the relationship between mathematics, information, and consciousness that extend far beyond physics. The resolution of the mathematical failure will be the most important mathematical achievement in the history of science. It will provide the mathematical language that nature speaks at the Planck scale. It will resolve the singularity. It will preserve information. It will reproduce the thermodynamics. It will unify gravity and quantum mechanics. And it will reveal the mathematical structure of reality at its deepest level. The connection between the mathematical failure and the nature of information is profound. If information is more fundamental than space-time, as the holographic principle suggests, then the mathematical failure at the singularity is a failure of the geometric description, not of the informational description. The boundary quantum state, which encodes all the information, evolves smoothly and unitarily. The bulk geometry, which is derived from the boundary state, develops a singularity. The failure is in the derived description, not in the fundamental one. The Ryu-Takayanagi formula, proposed in 2006, connects the entanglement entropy of boundary regions to the areas of minimal surfaces in the bulk. This mathematical connection between entanglement and geometry is one of the most important results in modern theoretical physics. It tells us that geometry is encoded in entanglement. The mathematical structure of the bulk, including its singularity, is generated by the mathematical structure of the boundary entanglement. The quantum version of the Ryu-Takayanagi formula, developed by Engelhardt and Wall, includes quantum corrections and leads to the island formula. The quantum extremal surface, which generalizes the Ryu-Takayanagi surface, is the mathematical object that produces the page curve and ensures unitarity. The mathematical resolution of the singularity is connected to the mathematical structure of quantum entanglement through these formulas. The scrambling time provides a mathematical measure of the information processing speed. For Sagittarius A*, milliseconds. The Margulis-Levitin theorem sets the maximum rate of quantum evolution. Black holes saturate this limit. The mathematical framework that describes the interior must be consistent with this maximum processing speed. The singularity, where the mathematics fails, is also the point of maximum computational activity. The page curve is the mathematical signature of information preservation, rising entropy during the first half, falling entropy during the second half. The island formula reproduces this curve. The mathematical mechanism involves quantum extremal islands that grow as the black hole evaporates, transferring information from interior to exterior. The mathematical failure at the singularity is resolved by a mathematical transfer of information from the failing bulk description to the well-defined boundary description. The arrow of time is connected to the mathematical failure through the Weil curvature hypothesis. The mathematical structure of the singularity encodes the thermodynamic arrow. The failure occurs in the direction of increasing entropy, in the direction of the future. The mathematical failure is not symmetric in time. It has a temporal orientation, reflecting the thermodynamic asymmetry of the universe. The concept of the Planck star provides a concrete mathematical replacement for the singularity. The Planck star has finite density, finite volume, and finite curvature. The mathematics is well defined. The physical predictions are finite. The mathematical failure has been replaced by mathematical success at the Planck scale. The infinite density is replaced by the Planck density. The zero volume is replaced by the Planck volume. The mathematics works. The connection between the mathematical failure and the nature of time adds another layer. General relativity treats time as a coordinate on a smooth manifold. The singularity theorems prove that some geodesics terminate after finite proper time. Time ends at the singularity. But if time is emergent, as the Wheeler-DeWitt equation suggests, then the ending of time at the singularity is an ending of the emergent description, not of the underlying reality. The quantum state continues to exist, static and timeless, even when the geometric time coordinate has terminated. The computational complexity perspective, developed by Susskind and others, provides a dynamical view. The interior of a black hole grows because quantum complexity increases. The mathematical description of this growth uses the language of computational complexity theory, a mathematical framework very different from differential geometry. The failure of the geometric description at the singularity corresponds to the point where complexity exceeds the descriptive capacity of geometry. The mathematical failure is a capacity failure, not a reality failure. The smooth manifold has a finite capacity for encoding quantum complexity. The quantum state of the black hole exceeds this capacity at the singularity. A different mathematical representation, with greater capacity, is needed. The holographic boundary theory has unlimited capacity. The smooth manifold does not. The failure is in the container, not in the content. The Hayden-Preskill protocol demonstrates that information processing continues inside the black hole at the maximum possible rate. The mathematical framework that describes this processing must be consistent with unitarity, with the thermodynamics, and with the geometry. These constraints severely limit the possible mathematical frameworks. The surviving frameworks all share the property that they produce finite answers at the center, replacing the infinity of general relativity with a finite, physically meaningful result. The Page curve, the mathematical signature of unitary evolution during black hole evaporation, has been reproduced by the island formula through a gravitational calculation. The mathematical mechanism involves quantum extremal surfaces and quantum extremal islands. These mathematical objects, which have no classical counterpart, are essential for producing the correct answer. The mathematical resolution of the failure requires extending the mathematical framework to include objects that the classical theory cannot see. The connection between the mathematical failure and the concept of information is perhaps the most important. If information is more fundamental than space-time, then the mathematical failure of space-time at the singularity does not imply a failure of information. The information, encoded on the holographic boundary, continues to evolve unitarily. The space-time, which is generated by the information, develops a singularity, but the information itself is unaffected. This is the deepest lesson of the mathematical failure. The mathematics that fails is the mathematics of space-time. The mathematics that succeeds is the mathematics of information. The fundamental mathematical description of reality is informational, not geometric. The geometric description is derived from the informational description through the holographic encoding. At the singularity, the derivation breaks down, but the fundamental informational description continues without interruption. The resolution of the mathematical failure will be the most important mathematical achievement since the development of calculus. It will provide a mathematical framework that describes nature at the Planck scale without producing infinity. It will unify the mathematics of gravity with the mathematics of quantum mechanics. It will resolve the singularity, preserve information, reproduce the thermodynamics, and reveal the mathematical structure of reality at its deepest level. The connection between the mathematical failure and consciousness raises deep questions. Consciousness, whatever it is, depends on information processing. If the mathematics of space-time fails at the singularity, does information processing fail there too? If information processing fails, does consciousness end? Thank you for watching. Or does consciousness, like information, persist through the mathematical failure, encoded in the boundary, preserved by unitarity, surviving the breakdown of the geometric description. These questions are speculative, but they are raised directly by the mathematical failure. The failure is not just a problem for equations, it is a problem for any physical process that depends on the mathematical description of spacetime. If the description fails, every process that depends on it is affected. The mathematical failure at the singularity is a failure that cascades through all of physics. The resolution will have implications far beyond black holes. It will provide the mathematical language for describing the very early universe. It will provide tools for understanding quantum phenomena in extreme gravitational environments. It will connect gravity to the other fundamental forces through a unified mathematical framework, and it will reveal the mathematical structure of reality at its deepest level. The next mathematics is coming, and when it arrives, the failure inside black holes will become the greatest success in the history of the human mind. The failure will become a doorway. The infinity will become a finite answer. The breakdown will become understanding. And the mathematical language that nature speaks at the Planck scale, the language that has been hiding behind the singularity for more than a century, will finally be heard, understood, and spoken by human beings. That will be the moment when mathematics, which has never failed before, succeeds again at the point where it once fell silent, and the silence will be filled with the most beautiful mathematics the universe has ever produced.